Hi everyone, welcome to the first CS188 section 1 walkthrough video. So let's just get started with the first worksheet problem, which is Towers of Hanoi. We can take a look at the description down here. Basically, for those of you who are not familiar with the problem, the way it works is, you have these three pegs, kind of like what you see in this image, and then you have these, donut-shaped objects which you can put on, which you can kind of put on top of each of these pegs. And the aim of this game is to get all of these donut-shaped things from the peg on the left to the peg all the way on the right. And the rule that you have to follow while doing this is you're not allowed to put a larger donut-shaped thing on top of a smaller one. So all the moves that you're allowed to make is basically, moving things, moving these objects from the top of one peg to the top of another peg, and all while obeying the constraint that you should never put a larger one on top of a smaller one. So that's kind of the high-level description of this game. And we're going to be formulating this as a search problem and trying to write a state representation as well as describing what those states look like and what the actions look like for this search problem, right? And just recall that a search problem is basically it's a way of formulating a problem in this class that the way you do this is by having states be represented by nodes in a graph, and actions you can represent as being the arrows or the edges between these nodes. And we can represent this as a graph and then perform one of the many search algorithms we've learned, like DFS or BFS or uniform cost search, to search this graph and find a solution, right? So let's just get started with the first subpart of this problem, that's 1a, which is to propose a state representation for this problem. So kind of, a good way to start with these problems is to just think of, naively, what is the bare minimum amount of information you need in order to capture all the information about the problem at any point in time. So if you were to take a snapshot of this game at some point in time, the question which you want to ask yourself is, what is the bare minimum amount of information that you need to be able to fully describe the state of the game, right? And in this case, I think one kind of good way to start is by just looking at this image and thinking, what do I need to describe this image, right? And I think, one kind of fairly natural conclusion is to say, well, suppose I assign labels to each of these objects, right? So, the smallest one, I might call it object 1. This one I can call it object 2, object 3, and object 4. And in general, if you have n of them, then it would go all the way from 1 to n, right? And once you've labeled these objects, well, then you can basically describe the state of the system by just saying what is the set of objects that is on the first peg, what is the set of objects that's on the second peg, and what is the set of objects on the third peg, right? Now, why is this sufficient? Well, we know that all of these objects are different sizes, right? Because you have the smallest one, next smallest one, the smallest after that, and so on and so forth. All of these are different sizes, which means that suppose I know, in this case, I know that objects 1, 2, 3, and 4 are all on the first peg. The thing is, once I have this information, I know what is the exact order that these must be arranged in on that first peg. Why? Because if it was not arranged in this order, with 1 at the top and 4 at the bottom, then I'd be breaking the constraint of the game, right? If I had it in the order of 2 on top and then 1, 3, 4, well, this does not obey the constraints of the game because I have a bigger object on top of a smaller object, right? Which is not allowed. Right, so kind of the crucial realization in this subproblem is to notice that once you know which objects are on each peg, you know what their order is, and so you know the entire state of the game, right? So what's the answer to part A? Basically, you want to maintain a list for each of the pegs, which describes what are the objects on that peg. So, we can just write that in words. So it's a list for each peg, which lists, listing all objects on that peg. And maybe if you wanted to write this in symbols, well, actually part B gives us a good opportunity to do that. So, so part B is asking us, what is the start state? Well then, the start state is just what we have up here, right? This picture is describing to us the start state. The end state is to eventually get all of these on the right-hand side, right? So from this image, what do we have as the start state? Well, it's exactly what we've described over here. It's the first list being 1, 2, 3, 4. So maybe one way to write this would be as a tuple, specifically a 3 tuple. That is, it has 3 elements, and each of those elements is one of the lists corresponding to one of the pegs. So in this case, the first list is the list 1, 2, 3, 4, like that. And what are the second and third lists? Well, they are just empty lists because you have no objects on the second and third peg. And yeah, let me put this bracket a bit closer. And that's it. That's what your start state is, right? Perhaps up here in part A, you could have written a more symbolic representation of what the state is. Maybe something like some sort of list comprehension or something like that. But it's not strictly necessary for this problem. The important thing is just to understand what this state representation looks like, right? So writing it in words would also be sufficient for this problem. Okay, let's head down to part C. From a given state, what actions are legal? Okay, so for this, once again, let's scroll up here, and kind of what piece of information in this problem description tells us what actions you can do. Well, it's the part which tells you about the constraint of the problem, which is that you cannot have you can't have a smaller object. You cannot have a larger object on top of a smaller object, and also you can only kind of pick things up and drop things from the top of these piles. So I can't, for example, do something like just take 2 from here and then put it over here because there's 1 on top of 2, right? So you can only lift and put down from the top of these piles. Okay, so how do I describe the actions then using this information? Well, I can just say, my actions are I can pop from one list and push to another. As long as it obeys the constraint of the problem, being that, as long as the one which you are popping as well as pushing is no larger than, or let's say smaller than, the one that you are pushing onto. And this also is kind of, it's a description in words. You could probably do this using some kind of symbols as well, but for the purposes of this problem, which is just to kind of understand state representations, it's sufficient to write this as a description in words, right? So we'll just leave it like this. And kind of note that we're using terms like push and pop, which kind of come from the the stack and queue terminology, and we're kind of using these words here to describe the fact that you can only take things and put things from the top of the lists, right? So you can't take something from the bottom, and that's why we're using the words pop and push to kind of emphasize this fact, right? Okay, let's head down to part D. What is the goal test? Once again, we can kind of look at the problem description as well as the image we have here. Ultimately, we want to have all 4 of these on the rightmost peg, and once again, they will be in the same relative ordering because, again, you can't have a bigger one on top of a smaller one, so it's going to be 1, 2, 3, 4, but it'll all be on the 3rd peg, right? What does that look like in terms of our state representation? It's similar to the start state, except all 4 of these are in the 3rd list, they're not in the 1st list, right? So if we want to write that down, it looks like the 1st list is empty, 2nd list is empty, and the 3rd list is 1, 2, 3, 4. And that's it for the first problem. Okay, so now let's move on to problem 2 of the worksheet, which is basically kind of mechanically running the 3 search algorithms that we've learned so far in the class, that is DFS, BFS, and uniform cost search on this sample graph over here. So you can think of each of these nodes as being states in some state space, and these edges as representing actions that take you from, say this state to this state and so on. And we are trying to find the best path from the start state over here to the goal state over here using each of these 3 algorithms. And we're just going to run through the steps of each of them and see how they work, right? Let's start with the first one, which is going to be DFS. So 2A. And the way that I like to do these kinds of problems is to actually write out what the algorithm is storing in memory at each point in time and solve this the way the algorithm would, right? So in particular, I like to write down this table where you have one column being current node, that is the current node or state that is being considered by the algorithm, and the other column is the fringe. Now, what is the fringe? Well, basically, it's basically what the name suggests. So at each point in time, the algorithm has explored some of the states in this graph, and then there are some states which are kind of immediately outside this range, right? So all the nodes which are adjacent to the nodes that the algorithm has visited so far, we call those part of the fringe, right? And it turns out that the way all three of these algorithms work is when they want to decide what node to visit next, they look at the fringe, and using some policy, they choose a node from the fringe. And the way these algorithms differ is purely in how they make that choice. So how they decide which of the nodes to visit next from the fringe, right? And now let's see, for example, how DFS does that, right? It starts out having not visited any nodes, so this column is empty, and it just adds the starting node to the fringe. For simplicity, I will call that S, right? And also there's one more thing which I want to maintain as I'm going through this algorithm, which is a partial kind of version of this graph, which only shows the states that I've seen so far. Now in this case, because I'm just starting out, all this sample graph contains is S, right? Okay, now what does DFS do? It looks at all the vertices or all the nodes in the fringe, and it visits the one. It visits something from the fringe, and in this case, because the fringe only has one node in it, it can only visit S. So this next one has to be S. Now, what does the fringe get updated to? Well, we add to the fringe all the nodes which are neighbors of S. So in this case, that's A, D, and B. So the fringe now contains A, D, and B. Let's not forget to update this as well. So now we have seen A, we have seen D, and we've also seen B, right? There's one more thing which I want to keep track of, which is also, what is the depth of each of the nodes that I have seen so far in the fringe. What do I mean by depth? Well, basically looking at this graph, what is the number of edge transitions, or you can think of it as being the number of actions which I took to get from the start state to that state. So in the case of A, D, and B, it's just one because they're all separated from S by just one edge, right? So for each of these right now, it's just one. And we'll see shortly why it's important to keep track of these, right? But for all of these, it's just one. And I guess for this, it would have been 0, right? Because the start state is 0 spaces from the start state. Okay, now why are these relevant? Well, the way that DFS chooses which node to visit next is using these numbers. So DFS looks at the things in the fringe. It sees which of these is deepest in the search tree. So it sees which of these has the largest number, and it chooses that vertex to visit next. Now in this case, they all have the same number. They all have 1, a depth of 1. So it has to break ties somehow. And in this case, the problem states that we break ties alphabetically. So A is alphabetically first, which means that the algorithm will visit A next, right? Okay, what happens now? Well, the neighbors of A get added to the fringe. In this case, the only neighbor of A is C, which means that C gets added to the fringe. So we have D and B with their old depth numbers, as well as you have C now. And what is the depth of C? Well, let's quickly update this partial graph here. Okay, now what is the depth of C? Well, it's 2 hops away from S, right? 1 hop, 2 hops. So the depth of C is 2. Okay, now what does the algorithm decide to visit next? Well, it's DFS, so it looks at these. It sees that C has the highest depth value. It's the deepest in the search tree, so it visits C. And what does it update the fringe to? Well, C, the neighbors of C are D as well as the goal state, which means the fringe contains the old D, contains the old B, and now it also contains a new copy of D, right? Now this new copy of D is what came from, this path which went from start to A to C and then finally to D, right? So we have to re-add D once again. It's like a different copy of the node D, and this time, what is the depth of this new copy? Well, it's 1, 2, 3, right? Because this path takes length 3 to get from S to D. So this copy of D has a depth of 3. And we also add G, the goal state. And what is the depth of that? Well, that's also 3, right? Because G is 1, 2, 3 steps away. Okay, note that we are not done yet. Even though we have kind of seen the goal state in the sense that it is on our fringe, the algorithm only ends when G appears over here on the left-hand side. So only when we visit G as a current node does the algorithm end. So for now, it's still going on. So what does DFS visit next? It looks at these. It sees that D and G have the highest depth values, and between them, D is alphabetically earlier, so it visits D. What happens to the fringe? Well, the neighbors of D are only G, so the fringe now contains the old D, the old B, the old copy of G, as well as a new copy of G, and this new copy has a depth of 4, right? Because it's the version of G that you got by going from S to A to C to D and then to G. So let's add this edge. And the depth of this is 4. And now the final step of the algorithm, it looks at these, it sees that this one has the highest depth, so it visits G, and at this point the algorithm is over, right? Because now you have a goal state appearing on the left-hand side, appearing as a current node, which means the algorithm has visited the goal state, and that's when it ends, right? So from here, if you want to reconstruct what is the path that the algorithm will return, well, just retrace your steps along the left column. So it's S, A, C, D, G. Let's write, okay, so that's S, A, C, D, G. And that's the answer to part A. Let's get started with part B then. And the way we're going to approach this is very similar to part A. We're going to have the same, kind of table over here. I'll just erase all the stuff from part A. Okay, so now let's start doing BFS. It's going to be the same process. The only difference is in how we decide to remove things from the fringe, right? So the first step stays the same. You start with no nodes visited, and you start with only S on your fringe. And then you visit S. You add the neighbors of S to the fringe. In this case, that's A and B and D. And each of these has an associated depth. In this case, they are all 1. Right? And let's also draw that here from the start state. We have A, we have B, and we have D. Okay. And now is kind of where these algorithms start to differ. So at this point, what is the next node that BFS chooses? Well, BFS is going to choose not whichever of these has the largest depth number, but instead which one has the smallest depth number. So BFS, or breadth first search, wants to choose the one which is shallowest in the search tree, as opposed to DFS, which chooses the one that's deepest. Right? That's kind of the key difference between these two algorithms. Okay, so what gets visited next? Well, in this case, it happens to be the same because they all have a depth of 1. So again, it's just tie breaking, and tie breaking happens alphabetically, which means that A goes next. Okay, so what are the neighbors of A? It's just C, which means now you get the old B, the old D, and you also get C added, which has now a depth of 2. Right? Oops, that should be a C. Okay. And now what does BFS do? Well, DFS would have chosen C because C is deepest, but BFS wants the one that's shallowest. So it looks at B and D, which both have a depth of 1, and between them, B is alphabetically first, so it goes to B. Okay, what are the neighbors of B? The only neighbor of B is D. So what happens is D gets re-added to this fringe over here, and it gets re-added with a different depth. What is the depth of this new D which is getting added? It's 2, because it's 2 steps away, right? Looks like, sorry, there's an error in this graph over here. There should be a D over here and a B over here. My bad. Which means now this edge has been discovered, and the D which we are adding has a depth of 2. Okay, once again, BFS looks at the fringe. It says that D is the shallowest, so it visits D. It looks at the neighbors of D. The only neighbor of D is the goal, which is G, which means our fringe becomes C and D and G, right? What is the depth of G? Well, it's going to be, we were previously at D, and this D had a depth of 2. Maybe I'll label these with the depths. So this D, sorry, this D had a depth of 1 because this was the one that we visited next. This B had a depth of 1. This A had a depth of 1. This S had a depth of 0. And what depth does this G have? It has a depth of 2 because we went from start to D and then we're going from D to goal. So this G has a depth of 2. Okay, so let's also draw the goal over here. So goal state, we have an edge from D. Okay. So now what does BFS visit next? It looks at these. They all have the same depth of 2. So it chooses the alphabetically first one, which is C. What are the neighbors of C? Well, it's D as well as G, which means our fringe gets updated with 2 new copies, one for each of those. So we have a D, we have a G. We have a new copy of D, which has a depth of this new copy of D has a depth of 3, not 2, because we went from start to A to C, and then C to D. So this copy has a depth of 3, and the new copy of G also has a depth of 3. Okay, and we are nearing the end of the algorithm because what happens next? Okay, so this step is kind of important because now notice that we have this fringe and the 2 shallowest elements are this D as well as this G. They both have a depth of 2, right? And because D is alphabetically first, what the algorithm would want to do is to visit D, right? But the issue now is that we've already visited D once before over the course of this algorithm, right? D has been visited over here. Now, why is this relevant? Well, the search that we're executing right now is BFS graph search as opposed to being BFS tree search, right? The distinction being that in the case of BFS tree search, you are allowed to revisit nodes that you have already visited in the past. Whereas for BFS graph search, you maintain this set which we call the closed set. Basically what that means is that you maintain a set of vertices that you have visited before. In this case, visited meaning it has appeared in the left-hand column, right? The current node column. And is D one of those nodes? Well, yes, it is, because it's right over here, right? And basically at each step of the algorithm, before we decide what to visit next from the fringe, a graph search algorithm will look at the closed set and it'll make sure that what it's visiting is not already in the closed set, to make sure that you don't revisit vertices. Which means in this case, it would look at D, it would say, okay, D is my best choice, but I've already visited D, so I'm going to pass on that, right? So it's not going to visit D. It's going to visit the next one, which is G. So the next one to be visited is G with depth 2. And at that point, we have a goal state in the left-hand column, and the algorithm has completed, right? So the BFS algorithm has completed as soon as it sees a goal state in the left-hand column. So we're done at this point, and what is the path that we return? Well, it takes some work to trace back the path that led you to this G. It's not as simple as just looking at all the nodes in the left-hand column. Instead, you have to kind of think about, okay, when was this G added to the queue? It was added over here, right? And what caused it to be added? Well, this row corresponds to D1, right? And when was D1 added? D1 was added over here. So D1 came straight from the source, right? Straight from S. So what's the path? The path that we have found is the path from S to D to G. And this is indeed a path of length 2, right? So what's our answer? Our answer is S D, G. And that's the answer for part B. Okay, now we're going to be doing part C. That's the last part, which is uniform cost search. Yeah, it's going to be the same process as A and B, except the way that we remove things from the fringe is going to be a bit different. And also, you might notice that, so far in DFS and BFS, we've completely been ignoring these edge weights, right? We haven't taken them into account at all. That's because BFS and DFS only look at, they basically only look at the structure of the graph itself. They don't look at what are the costs of these edge transitions, right? So, as far as these two algorithms are concerned, all of these weights are completely invisible. Uniform cost search is the algorithm which will actually end up using these weights, right? And we'll see how they will use them as we proceed with the algorithm. So, okay, step one is the same as the first two. You start with no nodes visited, and you start with S on the fringe. Now, there's going to be a slight modification to what we label each of these nodes with. So instead of labeling them with the depth, we're going to instead label them with the, let's call it the cumulative cost, right? That is, what is the sum of the weights of all the edges that we took to get to this node from the source, right? In this case, S is just the source, so, its label is still 0 because the cost of getting from the source to the source is 0. And what's the first step? Well, then we remove S from the fringe, we visit S, and we add its neighbors, which are A, B, and D. What are the labels? Instead of being 1, now they are each labeled with the edge weights from S to each of these nodes. So A is 2, B is 3, and D is 5, right? So here's kind of one difference you can see between UCS and the other two algorithms. Okay. Also, let's draw that down here. I'm going to redraw this a bit below because we might need more space for this table up here in uniform cost search. So I'll redraw this. B, it has seen A with weights 2 and 3, and it has also seen D with a weight of 5. Okay, now what does uniform cost search do? Uniform cost search is going to look at all of the nodes over here, and it's going to remove the one which has the lowest total cost from that node to the source or to the start, right? And basically that means it's going to look at these, it's going to choose the one which has the lowest number, right? If there's ties, it'll break them alphabetically. In this case, there's no ties. A is the one with the smallest number, so it's going to visit A. And we're left with B. This is a 3. We're left with D. And what are the neighbors of A? Well, it's just C. And now when we're deciding the number of C, note that we're talking about the cumulative cost of the entire path, right? So it's not just this 4, it's this 4 plus whatever the weight of A was, right? In this case, the weight of A was 2, so it's going to be 4 plus 2. And you can interpret that as being like literally the length of this path, right? It's this 2 plus that 4. So for C, the weight is going to be 6, right? Okay. Now it's the same process once again. It's going to remove B because B is the one with the smallest number. Let's add C over here before we forget. It's going to have length of 4 to this edge. Okay, we're visiting B. What are the neighbors of B? Well, D is the only neighbor, which means we still have this first copy of D, and we still have this C, but now we also add a second copy of D. What is the number associated with this copy? One way in which you can think of this number is also being a priority, right? Because we know that the way that the fringe is implemented in the case of uniform cost search is as a priority queue. So you can also think of these as being priorities, and I might use the word number and priority interchangeably, right? So what is the priority of D? It's going to be 3 plus 4, which is 7. Okay, let's add this. What is the next step? Well, D has this, it has the smallest number, which you can think of as being the best priority. So D gets visited next. We are left with C, the other D, as well as what are the neighbors of D? Well, G is the only neighbor. So we also get this G over here. And what is the associated priority? It's going to be 5 plus the length of this edge. So it's going to be 10. And let's add G. What comes next? C comes next because it's the next lowest. What are the neighbors of C? Well, it's D as well as the goal G, right? So we are left with the old D, the old G. We're left with a new copy of D. What is the number for this? It's 6 plus 1. So it's going to be 7. And the other copy of G, the number of this is going to be 6 plus 2, which is 8. Okay. Let's add in these edges. It's a 2 here and a 1 here, right? What next? Okay, now note that both of these D's happen to have the same priority, and they're also, these are both the next which would be removed by the algorithm from the fringe, right? Because they both have the lowest priority, or I guess they both have the lowest number, which is the best priority, right? Because you want to remove whatever has the lowest number. But the thing is, notice that we have visited D once before, right? D is already here in the closed set because it's been visited before. So the algorithm is not going to want to visit either of these Ds. So we can either, we can deal with that either by simply not visiting D from the fringe whenever it comes up, or for simplicity, I'll just kind of cross these out because I know that they're never going to be visited again, right? Since we already got D over here once. Okay, so what happens next? The algorithm looks at the fringe. We see that this G with a priority of 8 is the best possible choice. So it chooses G. And at this point, the algorithm has completed because we see a goal state which is in the current node column, right? So the algorithm is done. Now we just have to kind of retrace our steps and find what is the path that resulted in us visiting this G. And we get that by noticing, here we have the G. When was this G added to the fringe? It was added in this row, right? Which means it came from this C. Okay, when was C6 added to the fringe? Well, C6 was added to the fringe in this row, right? Which means where did it come from? It came from this A. Where did A2 get added to the fringe? It got added in this row, so it came from S, right? So kind of by keeping track of this chain of which node gave rise to which node in the fringe, we can kind of reconstruct the path, and we have that we went from S to A, and then A to C, and then from C to G, right? So what's the answer? The answer here is just S, A, C, G. And here's kind of the important thing about this. If you look at all possible paths in the graph going from the start to the goal, there's quite a few of them, right? You can go, for example, source to D to goal. You can go source B to D and then goal, or source A, C, D goal, and then finally the source A, C goal, right? If you look at all of these and you compute the path lengths of all of these using the actual weights on these edges, you will find that SACG is the smallest one, right? It's, what is it? It's 2 plus 4 plus 2, which is a path length of 8, right? And this is in fact the shortest path from S to G using these edge weights that we have, right? So what is kind of important or good about uniform cost search? The fact that it really does find for us the shortest path from S to G, right? And that's why uniform cost search is useful for us. Just a side note, uniform cost search is also known as Dijkstra's algorithm. Perhaps you've heard this term in other classes or just generally in other contexts. This algorithm and this algorithm are both exactly the same, right? Just in case you want to look it up online, this might be a good term to use to search for it. Also, one more note is, recall that when we did breadth first search, the path that we found was SDG. That's from here to here to here. In some sense, this is also a shortest path, although even though it does not take into account these edge weights, it is still the shortest path from S to G in the sense that it's shortest in terms of number of edges, right? Among all of the paths from S to G, SDG is the one that takes the least number of edges. And that's what's special about breadth first search, right? Breadth first search is optimizing for the number of edges in the path from your start node to your goal node. So in that sense, breadth first search is kind of like uniform cost search if you did not care about the edge weights, right? That's one way to think about BFS. DFS does not really have any guarantee. It's kind of a greedy approach. It just starts going down one path and keeps going until it can't go any further, then retraces its steps and keeps on going. So there's no kind of optimality guarantees from DFS. And as you can see, it gives us a path which is not good in terms of number of edges or in terms of total path length, right? And that's kind of a summary of how these algorithms work, as well as how you can mechanically do them. Of course, you don't have to actually work them out like this every time. Eventually, you might kind of get the hang of applying these algorithms without having to actually draw out an entire table, right? And as you practice this more and more, you will kind of get closer and closer to that point. So that's it for this video. Thank you for watching.